Started measuring for coefficient of static friction. Let's see here. We went ahead and placed it on a flat surface. So when I draw the free body diagram of the object on a flat surface, I'll say, okay, start right here, and let's go up 4. Now for this is mg and this is Fn. Now we notice that mg and Fn are equal and opposite. There's also another force. We'll put it right here. This is my static friction. Okay, that's what's keeping that mass in place, keeping it from moving. Now, I just drew it as a convention over on the left hand side, uh, but it could be on the right hand side. It just depends on if and when the object is moving. The object is not moving right now, so it doesn't matter. But the static friction, well, not static friction keeps it in place. Kinetic friction is going to move in the opposite the direction of motion. So what's going to happen is, or what happened in your lab, you're trying to determine the coefficient of static friction. So you're going to lift one end of your board, and the mass is going to feel the impetus to slide down. Now, where's that coming from? Well, let's draw another free body diagram. Here, that free body diagram, we said that we got 1, 2, 3, 4 down. That's mg. Same mass, same number of boxes. Now, here's what we got to do. We got to say 18 degrees this way. So 18 degrees puts me right about there. So I'm not going to draw it all the way out to there, but that's where the surface. So 90 degrees from that, that's my surface right here. Let me go ahead and draw that. Okay. So 90 degrees from that gives me this guy. Okay. That guy right there. Normal force is perpendicular to the surface. And since the surface is offset by 18 degrees, the normal force has to be offset by 18 degrees. So what happened here is just we turn the surface, the x-axis, 18 degrees. Now, we call this normal force, but noticeably, the normal force here and the normal force here on the inclined surface is not the same. So how do we find the normal force on the inclined surface? Well, we know the mg. That's one thing we do know. So what we can do is we can find the components of mg. That is Fn. That's theta right there. And then we'll just call this red another line. Okay? Now, here we go. Both of these deal with gravity. Whenever the side of the triangle is touching the angle that we're measuring, that is going to be cosine. So this side is going to be mg cosine theta. So we're going to say that Fn, excuse my left hand, is equal to mg cosine theta. Okay? Now, what force is pulling downward on the box? Well, the side of the triangle that's opposite the angle we're measuring is noted by sine. So this is going to be mg sine theta. So the applied force, the force that's applied that's pulling it down the incline, is mg sine theta. Now, let's remember the sum of the forces on the x-axis equals the applied force minus frictional force. And when they're moving at constant speed, or when they're not moving at all, the sum total of those forces is zero. So, if they're moving at constant speed, Fa must equal the friction, static friction, in fact. Okay? Now, if Fa equals the static friction, we'll put that right there. Now, to find the coefficient of static friction, Fs, remember, equals mu s times Fn. Well, let's do a little substitute. Fs is Fa, which is also mg sine theta. Okay? Now, that equals mu s times Fn, but Fn, let's substitute again, that equals mg cosine theta. Now, what we want to do is we want to solve for this guy. That's the guy we want to solve for, mu s. So let's divide both sides by mu s. Not mu s, by mg cosine theta. Now, here, mg cosine theta cancels out with mg cosine theta. Here, luckily, mg cancels out with mg. So we get mu s equals sine theta divided by cosine theta. So once you have your angle, and let's say it started moving at 18. So the angle that you're going to write for your data is going to be the one right before that, 17 degrees. So if that was the case, to find the coefficient of static friction, you would say sine 17 degrees divided by cosine 17 degrees. And after that, you get your handy dandy trusty dusty calculator out. Let's see. Number one, make sure it's in degree mode. Okay, we see right there. It's in degree mode. Clear. Sine 17 degrees divided by cosine. That gives us 0.3057. So we'll say 0.31. So that's our coefficient of static friction. So I would do that for each trial, and then afterwards, I would get a standard deviation. Remember, standard deviation is when we take, let's say, 0.31, 0.32, 0.30, 0.32, 0.32. Take them up, average them. 3, 7. Carry 1 divided by 5. I get 0.31. Okay, then 2 over 5. That's 4, something like that. 314. Okay, so that's my average, 0.314. And so I would say 0.314, 0.314. And so this would be negative 0.004, positive 0.006, okay, negative 0.013, 14, positive 0.006, and then positive 0.006, and then I would square all of these numbers and add them up, and then I'd stick them into that equation. 1 over n minus 1 average number squared square root, and that's my standard deviation right there. Formula